Okay, so today we're going to do modeling on radiation and natural convection. So what we're going to do is that we will use a surface-to-surface S2S radiation model in ANSYS Fluent, and we will set the boundary condition so that we can solve for natural convection and radiation. And also we're going to display the velocity vector and contour of our wall temperature, radiation flux, and so on in our results. Yeah? So this is our problem description. So we are having a cube, and this cube is having 6 faces, and one of the faces is aluminum wall. And this aluminum wall is heated to 473.15 Kelvin. The ambient temperature is 293.15 Kelvin. The size of the cube will be 0.25, 0.25, 0.25. And in this case, we'll consider the gravitational force, which is going down. So this is the global axis for our case study here. So, and then the dimensions given in this slide here. Yeah. So we have aluminum in one faces, and other faces is made up of an insulation material. It is subject to radiative and convection heat transfer to the surrounding, which is 293.15 Kelvin. Gravity acts downwards, and medium content in the box assumed to not to emit, absorb, or scatter radiation. All walls are gray. Yeah? So, and also we will use a surface-to-surface model in ANSYS later on. And for a working float, we have a plate number of 0.71. Rayleigh number is based on L 1.25. A length of 1.25 will be 1 times 10 power 8. This means that the flow is mostly laminar inside our scenario here. The Planck number given by this equation, K divided by 4 sigma LT power 3 is 0.006, and measures the relative importance of the conduction to radiation. Okay, so before you start, you need to go to Moodle and download a zip file called radiation natural convection zip. We have a file there, so there's a radiation.mesh file inside there. So later on, when you open up in ANSYS, you will see this mesh file like this. So let's jump in our ANSYS workbench. Before you start, remember to save your project. So I will go to my projects file here. I will name it as a 3D box. Yeah, save. Then after that, we're going to open up our Fluent. So go to the toolbox here, double click Fluent, and name as maybe 3D box for the convection and radiation. And then go to setup. So in this case, we'll use a 3D dimension, and we'll use a single precision. And make sure your display mesh is activated, and we'll use a serial processing option. Then click OK. You open up the Fluent solver engine. After done, we will import our file, a mesh file. So go file. We will import a mesh file. So we need to go and find our file. So redbox.mbs, yeah. So in the console here, you will see a cube like this in the window, mesh window here. And then if you roll up the console here, you will see that this consists of 64,000 hexagonal cells, yeah, for this object, yeah. All right. Then the next, before we move on, we need to check the mesh. So go to the setup domain here, mesh, and click the check. So what is important here is to make sure that the minimum volume in the console here, your minimum volume is a positive value. Yeah. And then we're going to set up our solver already. So go to setup general. So you see a general the property here. This case, we will use pressure base, steady, and then we will use absolute velocity. In this case, we will consider gravity in our case. So gravity is in the y direction. If you go to global axis here, y is pointing down, so we have a negative 9.81 meters over second square. We have done with the general setup. Then we go to our model, make sure the energy is on. And then in this case, we'll other is off. We will consider models for radiation. So go to radiation, right click, model. We'll use surface to surface. So radiation model window will come out. Make sure surface to surface is selected. And then model is off. There's an explanation on surface to surface in the PowerPoint slides. So this page, so go ahead and read this page. Yep. So you can pause and read. We'll continue with our simulation. So the next one, you go to setting in your radiation model. Go to setting there. And then we will remain as 1 for the phase per surface cluster for flow boundary zones. So this tutorial, we will see the effect of changing this number later on. I'll do one set for number 1 for 1 phase per surface cluster. I'll do 1 round, and then I'll do in the maybe second video for comparison. All right. So this is we put in 1 here, and then click apply to wall. Make sure ray tracing is activated. So click OK. So once OK, you go to compute right read here. You need to save the file. And the file we will name it as radiation 1.S2S.gz. So it's important to include .gz because once you because it will help you to it will ask the computer to go ahead and compress the file if you have a large file. So when you have a .gz behind, it will go ahead and compress the file for you. Yeah. So for small file, you can provide a .S2S after the radiation here. Yeah. So again, the purpose of having .gz is tell the computer to compress the file for you. Then click OK. So once done, I will click OK for the radiation setup. So we have done with the model. The next one is material. So we'll open up the setup, go to material, and then open up the float here. We go for air, right click edit. We will edit the air property. We will use the density, ideal gas density, and then we will change the value for your CP, thermal conductivity, and so on. Again, 1.01 for CP. Thermal conductivity is 0.0371, and we will change the viscosity value. Viscosity value to be 2.485 e power 5. Molecule weight we will maintain. Yeah. So again, all these value, when you use for your projects, you need to refer to material handbook and to see what is the value for your projects. So in this case, I key in according to the projects as an illustration. After you're done, you click create and then you close it. Next, we need to create a material for our installation material. Yeah. So again, okay, let's go ahead and go to our solid here. Expand it, go to aluminium, go to edit. So we need to create a new material. We call it insulation. Delete the chemical formula. And then we will key in the density here. So 50. Right. Thermal conductivity will be 0.09. And again, the property here, you need to refer to material handbook or the material that you use for your projects. Yeah. So click change and create. So it will ask you whether you want to override aluminium. Click no. Yeah. So if you click yes, then it will override the aluminium properties in the software. So later on, you need to key in back. So in this case, we click no. Then close. So you go to the tree here, you will see insulation material was created. So in this case, we have two types of material in our case. One is the aluminium at the back here. And then we have a 1, 2, 3, 1, 2, 3, 4, 5. 5 faces is insulation layer. Yeah. So the next one, after we're done for the material, we will set up for operating condition. So there's no operating condition at the tree here. You need to go to set up physics, go to operating condition. So in this case, what you need to set up is that make sure that we were specific for operating density and put in 0 for our operating density here. Then click OK. After that, we will go for boundary condition. So you open up the boundary condition, you will see default interior and W high X means W means wall. So you have 1, 2, 3, 4, 5, 6. You have a wall high X. What mean by wall high X or W high X? You look at the global axis here. If it mentioned wall high X means it is in front of the x-axis, so is this refer to this face. So this is wall high in x direction. At the back there, you have aluminum plate for these faces. At the back there is a wall low x. So we have low and high. Same with other faces. For example, y. These faces that I'm selecting here is wall w y direction high, and then the ground there is W Y low, and then this face is W Z high, and this one is W Z low. So this is how you identify the 6 surfaces here. Okay, we need to identify the boundary condition. So we go and set up the aluminium first. So not aluminum, these faces insulation layer here. So go to W high X, which is this face. So go and edit. So we will need to change some property over here. So go to thermal. Make sure that the material is changed because this 5 faces is insulation layer. So go to the material name there, change to insulation. And then we have a mixed thermal condition here. Key in 5 for thermal transfer coefficient. Free stream temperature will be 93.15. This given by the problem statement. 0.75 for external emissivity. External radiation temperature will be 293.15 also. Internal emissivity is 0.75. No, is 0.95. wall thickness is 0.05 meter. So again, all this value you have to check with the handbook or the material that you use for your projects. Yeah. So click OK. The next one, you're going to copy the insulation property to all the wall. So you will copy the property for W high X copy. We will copy W high X insulation property to the Z component, the Z faces. We select wall high Z and wall high low, which is this one and the back here. Okay, then click copy. It will ask you whether you want to copy. Click OK and close it. So we have set up the front here and then the Z here. We need to set up the Y. So you go to let me see here. So we go to high-low wall low X here, wall low X here. Right-click, edit. So you can see, go to thermal. So you see that the low X there, the low X is the aluminum plate, which is at the back here. So the material is aluminum, which is correct, yeah, which is correct. Then we will do the setting for aluminium. We will control the temperature. So temperature will be 473.15 Kelvin. This one you need to refer to the problem statement. Emissivity is 0.95. And then the wall thickness maybe remain as 0. Yeah. Okay, then you click OK. So we're done for the setup for aluminum plate there. Then we set up for our Y. So go to high Y, right click edit. So you see, you go to thermal, you will see that your high Y, which is this one, is aluminum, which is wrong. It's insulation. Change to insulation. And then we have a mixed flow. And key in the value 3293.15. External emissivity 0.75. Temperature external is our ambient pressure. Emissivity 0.95 for radiation. Thickness of our insulation wall is 0.05. Okay, then okay, everything's look fine. Then click OK. Then we need to copy this property to another side. So go to copy, click this one, copy. We'll copy the W high Y to the low side. It's at the ground there. Then you click copy. It will ask you whether you want to copy. Okay, close it. So you can check, yeah, you can check whether the property is correct or not. All right, insulation value. You can key in one by one, but what we do is we copy the same property to over another one. We have done with the boundary condition. The next one, we will obtain the solution. So we go to method here. We will use a coupled. And then we will, for the pressure, we will use the body force weighted, and we'll keep all the density, momentum, energy for the second order upwind. Yeah, and we'll activate the pseudo transient over here. And yeah, we're done for method. After that, we will set up for the conversion criteria. How you set up the conversion criteria, we need to read from the residual. So you go to solving. then residual. We need to monitor the residual, the activity of our calculation. Make sure the plot is checked. And then we will increase the absolute criteria here. For 0.001, we add one more decimal for accuracy. Yeah, for accuracy. For XYZ, energy will add one more decimal for accuracy. Conversion criteria absolute and scale, and click OK. Then we'll initialize our hybrid initialization. So go to initialization, select hybrid, and then click initialize. So you'll see in the console here, hybrid initialization is done. Then we need to check, we need some help to check for convergence. One of the method is to, with the help of the surface report, to judge for the convergence. Yeah, it's a good practice that you select a surface for convergence. So we're going to create a new surface named as ZZ center, Z for convergence. It will at the center of our cube. So we go to setup domain, and then we go to surface, go to create an ISO surface. So ISO surface window come out. We will going to select mesh for surface constant for mesh. And then we're going to select Z coordinate. All right. After that, we will ask the computer to compute the size of our surface. So the computer compute is at the center of the cube, where the total length of our cube is 0.25. So we have negative 0.125 to a positive 0.125, right? With a correct value. And we will go here and save as a new surface name. This surface is ZZ center of, yeah. And you can click the manage to delete the previous surface name is already defined. Yeah. Then in this case we need to create. Then close it. Yeah. Okay. So after that, we will create a surface report definition. So go to solving. Then go to report and definition. New surface report. We will look at area weighted average. So again, the area, surface report will pop up. Change this one to surface monitor 1. And we'll look at area weighted average, and we'll look at ZZ center, Z surfaces with at the center of the cube here. And it's good to track the report plot and print to console. We will see something on the console here. And if you want to save the file, you can check this one, but I want to save my hard disk, so I will not save the file at this moment. Yeah. So after that, okay, be careful on the field variable. By default, it will go for pressure. We want to see temperature. Yeah. Okay, so everything seems fine. Temperature selected, surface selected, report plot console. It's good. Then click OK. The next one, we will run the file. So before you run, we save the case file first. Export the case file and go and find your working file. So name as radian case for case A 1.cas.gz. Again, if you use the .gz at the back, it means you ask the computer to compress the file for you after you press OK. Yeah, okay. So now I have the data in my hard disk already. So I will ask the computer to calculate. So go to run calculation. solving, run calculation, advanced. So you will see run calculation page here. So click the user specified and we use the pseudo transient time of 1. We will run for 400 iteration and then we'll see whether we reach convergence. Right, once you set up this one, click calculate. So surface monitor output is coming out. So we are looking for the behavior of convergence. So how you know that you are reaching convergence is that you're having a straight line at the end of the iteration. So we ask the computer to track for 400 iteration. So let's see, and of course you expected to reach convergence in this case. Yeah. So we wait for the computer to run until 400 iteration. So it will take about maybe 1 to 2 more minutes. You can fast forward this video for the next steps until you see the video showing 300 or 400 iteration over here. However, you see from the curve here is decreasing, which is a good sign. And it starts showing some straight line here, although it seems like a curve, but it will start showing some straight line at the end here. So it is a good sign. This is what we want to see. And then for if you open up the scale residual, you see some activity over here. Yeah. So go back to the surface monitor. And again, this value is the temperature at the center of the cube. Yeah. We define to check the temperature at the center, whether we are reaching convergence. You see, the line is reaching a straight line. This is a good sign. Okay, so the calculation is completed. Click OK. So you check the curve of the iteration, it is flat. And you go to console here, you will say that solution is converged at 315 iteration. So the solution is converged. So this is a proof. You need to show to your examiner if this is your projects. So this file is important. You need to download this picture and put in your report and to show what happened in the console there, showing that the solution reached convergence at a step of 315. Okay, so we will save the case and data. So export the file for future reference. So I will save my file as radiation case A 1 dot case dot gz. Again, I put in .gz to ask the computer to compress the file for me. Okay. Okay. Then we want to activate the post-processing. At the side of the window here, there's a people facing a monitor. Left click this one, we want to see post-processing. So you see a cube in this window. Again, select post-processing. And then you rotate the cube a little bit so that you will see what happened in the post-processing. Okay, we are at the post-processing stage. So to see the result a bit clearly, we need to turn off the light in our graphic. So go to results here, graphic, and then right click, light. Wait for maybe 4-5 seconds. The light window will come out. Right, so light is just a illustration. We don't want light, so turn off the light, then click apply, close. Then we go to create a new surface for this cube. So go to post-processing, surface. You need to create a new surface, create a line rect surface, and we need to key in some value here. We want to create a surface contour at the center of this one. In this case, we use line rect surface to look at the temperature. So we need to define two endpoints. So we look at negative 0.125, 0, and this one is positive. This one is 0.125, 0.125. Okay, and then change the surface name to ZZ Excite for the new surface name. Oh, maybe. Then you click create, yeah. Then close this one. Then we're going to display the static temperature of contour. So go to post-processing, graphic, contour, edit. Yeah. So here we will check the fill so that later your contour will fill with color, and we will uncheck the auto range and will key in from 412 Kelvin to maximum 473.5 Kelvin blended, and we're going to show data at ZZ center, this one. Okay, and yeah, we're going to show contour of temperature. So go and change the temperature, static temperature, and once everything done, you click display. Yeah, so this is the surface of that one. Okay, you're seeing a surface at the plate there, so you can check the draw mesh here. Draw mesh, and yeah, make sure that the outline is checked for the edge type. Close, and then you can click the display again. So you will see that the contour is at the center of the cube, and if you look at the global here, your X low here, the red color is your aluminum plate. So the temperature for your aluminum plate is 474 Kelvin, and the minimum temperature you have over there is 421 Kelvin, and there's a radiation and convection process happen that transfer the heat over here. All right, so this is how you display the temperature. Yeah. Then the next we are going to show the temperature of our wall temperature of our cube. We have 6 faces, so you want to show the temperature for our 6 faces here. So go to post-processing, graphic, contour, new. So this one we will show the contour of wall temperature. Right, remember to set as temperature, yeah. So by default, some software you will go for pressure. We are going to set as a temperature. Make sure you check the fill and uncheck the node value. We'll use auto range in this case. No, not auto range. We will use temperature 413 to 473.15. And we're going to select all the wall surface, W, all the W represent wall, including the Z center, right? Then click Save and Display. So this is the wall temperature that that you can see. So if you click the cube, you rotate the cube. Yeah. So again, the X low here, the red color here is the aluminum plate. The static wall temperature maximum is 473 Kelvin, and you're having quite a colder temperature over here at your insulation plate here is 413 Kelvin over here, and you can check over other sides here, right? Okay, so we are done with the wall pressure, wall temperature, sorry. The next we're going to show radiation flux, heat flux, yeah? So go to post-processing, graphic, go to contour, and we're going to edit. We're going to show our wall flux. So contour of wall flux. And we're going to see radiation flux, heat flux. And this time we're going to ask the computer to auto range for us. And yeah, make sure you select all the wall because we want to see what happened to the wall, including the Z center. Yeah. And then we display. So this is the radiation heat flux that happened to our surface here. So if you rotate the cube, you'll see what happened to the radiation flux. So aluminium is radiating at 882 watt over meter square, and other surfaces also seeing some value there, but you have a negative value, most of the insulation surfaces here. Okay, so this is how you show the radiation heat flux. So when it comes to your assignment, you need to capture this photo, save picture, and then put in your report. Yeah. Okay, the next one is we want to display our velocity magnitude. So go to post-processing. We will go to graphic vector and edit. So we want to see what happened to our velocity here. Air velocity, yeah. So velocity, and we want to see what happened at the center there. Center. And make sure the draw mesh is activated, yeah. Then you click display. So you see there's a low dense of your arrow here. You can increase the presentation by go to scale here, increase to 7 maybe, then click display. You see the arrow is enlarged by a certain magnitude. So we can zoom in and zoom out. So there's a velocity, air velocity going up here at 0.2 meter per second, right? With agree, where the hot air will go up, right? Hot air will go up. We agree with the hypothesis. So we have done with the velocity presentation. The next one, we're going to see the value of our view factor and also radiation emitted in our process. So go to post-processing. And in the post-processing ribbon here, we have a S2S information. We want to extract the radiation information. Again, report option, activate view factor and activate incident radiation. And then we will select from WX, high X, to the rest of the wall. Yeah. And then after you press compute, something will happen to the console here. So the view factor is around 0.2, which is a good value. 0.2 is good value for a square box like what we have here. And if you're using a different domain, different size of domain, you need to check handbook and other industrial handbook to verify that you are getting the correct view factor value here. The next one we're going to look at. Okay, we're going to look at the heat transfer rate value. So go to post processing, Go to report here, look at flux. So this window will tell you the exact value of your mass flow rate, total heat transfer rate, and radiation heat transfer rate. So we look at the total heat transfer rate first, and we're going to look at all the wall value. What is the value? So you select all these, and then you click compute. So it will calculate for you. It will show you the value. So for at the wall, for example, wall high X with this wall high X with this in front here will be 12 watt. All right. So you will see that the energy imbalance here will be around 0.004%. Yeah, keep the net result here much lower. Yeah. So if you want to only see the total heat transfer for another phase, for example, want to see what happened to the low X there. Low X is your aluminum plate. Yeah. So you click compute. So you are having a heat transfer rate at around 63 watt. 63 watt from the aluminum plate over here. Yeah. The next one we will see the radiation heat transfer also. So we go click and click radiation heat transfer rate. We will see all the wall, what happened to all the wall, what the value for radiation heat transfer rate for all the 6 wall. So you click compute. So you see all the value come up here, and you will see that there's an imbalance here. So make sure this imbalance is a bit low. Yeah. So in this case, we have a 0.007 watt imbalance, right? So quite a good value, right? So if you only want to see what happened to the aluminium radiation heat transfer rate, so you just select the aluminium wall, which is a W low X. So you just press highlight this one and compute. So your radiation heat transfer rate for your aluminum plate is radiating at about 51 watt there. Yeah. So the next one we want to see a plot for XY plot for temperature. So you go to post processing, and then you go to XY plot and edit. So in this case, we want to see the temperature. So go to y-axis, change to temperature, and we want to see the wall temperature. Wall temperature. And then we want to see at the ZZ side there. All right. So then after that, click plot. Okay, so we have a temperature at the X side. So if you check the value position, this location to this location, total length is 0.25, is correct. So you have a negative 0.25 to 0.125. So if you look at the aluminium position, which is negative 0.25 X direction, you're having the temperature at the wall of the aluminium will be will be around 460 Kelvin at the wall here, and it will start to decrease as we reach to insulation plate here. It will reach around 400, maybe 420 or 25 Kelvin about here. So it dropped around 30 Kelvin. Yeah. So this is how you check the temperature of the wall. Right, click close. Then we will save this case file as case and data file. Again, go to your working folder and save this one as radiation B case 1 dot case dot gz. Again, dot gz, you will ask the computer to compress the file for you. Press OK. So we have the file. So I already show you how to look at the temperature profile of the wall what's the radiation value for that one. So I will stop the video over here, and I will show you in the next part to do comparison. We'll run for different scenario to make comparison. I'll stop the video here.